there. We'd be there. We have like 2 steps here left. I need to replace sine of theta and cosine of theta with x's. One of those you can do immediately because of the original substitution. What did we know in the original substitution? We actually did it right up here in the white box, the second line of the white box. Don't we know sine is equal to x over 3? So in place of the sine here, I can put x over 3. All I need to do is I need an expression for cosine to fill in there, and I'm done with a little simplifying. The problem is, do I have anything anywhere that's going to tell me what cosine was? It was my dx, but that was a derivative. I'm not doing a derivative here. In trig, what should you do when all else fails? Draw the picture of the triangle. I told you this is 80% of the trig you ever learned in one problem. Problem is I'm out of space. I think I'm going right in the middle, yeah, okay. So we're doing all variables here. So you may draw it in any quadrant. I always just draw them in the first myself. Okay. Which 2 sides do you know because of this original fact that we know that sine of theta is equal to x over 3? Opposite over hypotenuse, or you know y over r, whichever way you want to look at it. So I would know I have side x, and r was 3. So then how do I get the third side? Pythagorean theorem. Okay, what does the Pythagorean theorem say about this? Since I need the in long form, I'm going to call that some unknown letter. What's a letter we never use? M. Okay. The side we're missing is m squared plus x squared equals 9. Would you buy that? Yeah. So then x squared equals 9 minus m squared? And then I need to square root it. Can I break that down to 3 minus m? No. I cannot, because you can't break down into big terms. That stays square root of 9 minus m squared. Okay. Notice, how does that relate to the original problem? Okay, I shouldn't do, sorry, I should be 9 minus x squared, sorry. I was going to say I shouldn't have m's in there, I should have x's in there. The original problem had 9 minus x squared. Okay, when you draw this picture, you must get that original quantity back that you started with, or you have screwed it up. Okay, so if you started with 9 minus x squared in the original problem, you'll end up with that same expression over here when you draw the picture. Well, you better know which side it is. So now you have the picture, you need cosine out of the picture. So what is cosine out of the picture? You can do x over r, or you can do adjacent over hypotenuse, whichever one floats in your brain the best. Either way, side x or adjacent is the square root of 9 minus x squared. Hypotenuse, or r, is 3. And look, it's all x's again. It looks nasty. We better clean it up a little. Okay, the first part you can't change much. We need to distribute 9/2 times that inverse sign, so it's just going to sit there. Okay, now, over here, when I multiply those 2 denominators, I'm going to get 9. If I'm timesing by 9/2, the 9's are going to cancel, aren't they? So I'm only actually going to have a 1/2. X times the square root of 9 minus x squared, and then a big giant plus c. Oops, yeah, no, we're done. I copied it right. And it was, yes, that whole 9 minus x squared is under the square root. Wasn't that awesome? It's like the ultimate trig problem. If it's open, if it's this long problem. Yeah, this one is the page you said. Somebody could. Unexpected good style. But if you recall, actually let me pause this while we do. feelings about this, we'll move on. About the same. Actually, maybe a touch shorter, possibly. I don't like that color. Let's go a different color here. Next one. Similar, maybe not quite as much, but close. Okay, now, what you are looking at on these when you're deciding which substitution, it doesn't matter whether there's a root or not. All you're looking for is you'll have a number plus x squared plus a number, or a number minus x squared. It really doesn't matter if it's in a root or not. In this case, I have x squared plus a number.
How many lines is this one? 12. How many more slides do you want? Good for pages. So we're almost done?
I have one more. I have one more full problem to do, and then I'm going to show you shortcuts.
Oh, let's do shortcuts first.
No. I shouldn't say shortcuts. What's to do when you get the problem down to a point and you're trying to get those thetas back into x's? There are different situations that can happen when you want to get the thetas from back into x's. And so I need to Yes, you will. I am confident you can do it. They've done it every other year, and you are equally as brilliant. So, is this a sine, a tangent, or a secant?
It's a secant.
It's squared, and they're added. The only one that adds is tangent. So it's a what number tangent? Because you've got an x squared plus 4, so that's going to say the number I'm squaring on the 4 is going to be a 2 tangent. Because the beauty of it is, when we substitute it into that part where the x squared plus 4 is, it's going to turn out to be one of our fundamental identities. That's what makes this all click. That's the good news. Okay, while we're at it, though, since we're going to have to replace it, I recommend right now you go ahead and figure out what the dx is going to be, because you're going to need it right away. What's the derivative of tangent? Secant squared. So, what am I replacing? Every single x is being replaced. So when you square x, it's going to be 4 tangent squared. And then on the inside of the root, it's going to be another 4 tangent squared. Plus 4. Got lots of 4s. And then my personal mistake when I do these, if I'm going to screw this up, I'm going to screw it up right here. What else did I need to change that I haven't changed? The dx. I forget to sub the dx in. So that's going to be a 2 secant squared theta d theta when I put the dx in. So, what can I pull out front? At least help. I can pull a 2 and a 4. Okay. And so, from the inside, I can also, there's a 4 in common on the inside, but when I take it out, it's going to be a 2, so I'm going to have another 2 that comes out of there. I took out, on the inside of the roots, there's 4s, so I can pull the 4 out of there, but when I square root it, square root of 4, when I take it outside the root, it's going to become a 2. Well, subtract that, or I can write this in, I can say I'm taking out 4 tangent squared plus 1. So the square root of 4 becomes 2. The tangent squared plus 1 is still inside the root. Okay, and actually, just for space sake, it's okay if I write the 2 secant squared on top now? It just... Oh, the 2's gone. Sorry, it's just secant squared. Thank you. We pulled the 2 out front already. And so d theta is just hanging around back there doing its thing. How did I get from a 1 to a secant? All I did is I just took this secant squared, stuck it on top instead of way out there. It just takes up less space when I'm writing it, that's all. Okay, what fundamental identity is screaming at you? Use me! Use me! Yeah, tangent squared plus 1.
It's already tangent squared, so you just write Calm down.
She's right. She's ahead of the game here. Tangent squared plus 1 is secant squared. Okay, that secant squared is in the square root. So therefore, the secant squared, when she takes it out, which is what Ashley was telling me, that secant squared becomes just a plain old ordinary secant to the first. And out here in front, I have just a 1/4 left at the moment. Have a secant squared still on top. What can now cancel? One of the secants. Yes, we can ditch one secant. So secant is gone. One of them is gone. You can't see that color. Blue, yellow. And so what's left? There you go. 1/4. Secant over tangent squared. Okay. This is one of those special situations. You'll end up in a lot of problems with the secant over tangent squared. On page 3 of your journal is where I have you fill in the tips of how to remember what to do when you run into these different situations. You should find one on there for what do you do when you get a secant over a tangent squared. Okay. We are about to figure out what should I do when I get a secant over a tangent squared. Okay, Ellie is suggesting we could change tangent into a secant squared minus 1 using identity number 7. Will turning it into 2 terms help me? Do I want 2 terms on the bottom of a fraction? Probably not. That's another identity or 4 identities we could use here. Change it all sines and cosines. Yeah. So you need to change it all to sines and cosines. And then we'll get somewhere, I'll just say we'll get somewhere else. Now, when I change that tangent, what's it become? Thank you. It becomes a sine squared over a cosine squared. Okay. Now, it's algebra. What do you do? Yeah, because I can multiply by the reciprocal, I can flip those babies. I have a 1 over cosine times a cosine squared over a sine squared. Which means I canceled 1 cosine. So, what do I have left? Okay, I'm going to save that space. I need to get here where I can see what I've got. So we still have a 1/4, a single cosine over a sine squared. So changing that into sines and cosines, well, it changes it into sines and cosines instead of secants and tangents. But there's something you can do now, calculus-wise, that you've done many times before. You can use this one now. Okay, for what you write on the secant tangent squared, yeah, change the sines and cosines, or just show the sines and cosines, and you get to this. Because then you'll notice you have this on your list too. You should have cosine over sine squared on your list next. Before it? Okay, I don't know what order I put it in. And so now when you're going to do this, what am I going to use subs for? The sine or the cosine? The sine, it's on the bottom and it's squared. And you will actually be surprised at how this turns out pretty sweet. So now I'm doing a normal, now notice, we went from x's into thetas, and now we're going to u's. How cool is that? 3 variables in 1 problem. I have 15 seconds? Ah, boogers. Okay, well, we'll write this. Are we having fun yet, Dylan? I don't want to know what he's saying.